So this is part 2 of special interconnectivity, and I'm going to go over the mathematics of special interconnectivity. So the first thing we discussed was entanglement and how special interconnectivity works with entanglement. The second thing we discussed was teleportation and how special interconnectivity works with teleportation. I could talk about all day what particles are made of, and I can talk about patterns of space-time and actually build models, and I have done it, of how these objects are made of space-time. But nevertheless, that doesn't defeat the purpose of special interconnectivity, regardless of what particles are actually made of. It's just showing the effects in space-time that's going on between the particles. And this is going to be the entire basis for the mathematics that I'm going to have to create. So, this is going to be free-handed as well, but I'm going to be pausing throughout the video to make sure I get it absolutely correct. So going back, looking over some stuff, this is not, well, in quantum mechanics, but rather I pulled it from the Angular site, L2, LJ equals 0. And that would stand in entanglement as well. But to reiterate, because they share interconnectivity, there'd have to be a slight elaboration. In the complex numbers, we'd have to come up with a conjugation that put them at half. And basically, it would be this is gonna be particularly weird. You don't normally do this with quantum mechanics, but I'm going to do it anyways. And that is going to be L2 comma LJ divided by 2 plus or no, divided by 2 times 2, and that seems rather numb and nullified, but there's a good reason for this breakdown. It's because eventually you're going to lead to half the formulation when you break it down. And so the angular momentum solution should be halved because the mass would be twice as much. So when a force is applied to an object, like an electron, to give it angular momentum, I'm suggesting that that momentum will be slower than given with a, it would be slower with a regular electron as opposed to an entangled one. And my proof for this, my evidence for this, is in, this is going to seem bizarre, and it doesn't necessarily tie back to entanglement, but it will eventually. So let's talk about superconductors and quantum locking. In quantum locking, if you, one sec. Sorry, I took a breather. In quantum locking, if you were to add the weight, if you were to take the weight of an object and put it on a scale, then you have the weight of the object. And if you had an identical object and put it on a scale, so basically LB scale equals LB2 scale. And you were to quantum lock them, the weight would be actually added together, multiplied, not divided, not cubed, squared, whatever formulation you wanted to make. To put in simple mathematics, the weight is literally added together, and so it would be LB scale plus LB2 scale equals quantum locked scale. And that is as basic as it gets. And that occurs within quantum locking. So it is my position that you would have to get this result for angular momentum, and in classical mechanics, the result would be the same divided by 2. The result would be the same divided by 2. And the breakdown would be two formulations of this that both end up together in conjunct a complicated what is it? Sorry, the phrase escapes my mind, so I'm not going to sound like a fool. But there would be two counterparts that both would equal 0. And that would satisfy momentum in quantum mechanics. They would also satisfy angular momentum. That would also satisfy other things that we still have yet to study. So basically, how much force can we apply to an electron to get it to move, however fast, and what is the lightest amount of force we can do so it doesn't go the speed of light, if you will. And then apply that to an entangled electron, and you should have different results. You should have different results as opposed to the unentangled one. And it is my prediction, even though I know that it's going to be somewhat wrong, but I'm going to make the prediction anyways, that the electron half the I want to say in totality half the velocity or half the momentum, because the mass for electron A is equal to the mass of electron B, and that's also equal to a random electron C. Their masses are always equal, even though they were split in two. This is really important to understand, because that means that A and B equal C times 2. The A plus B equals C times 2. And that is very simply put. I'm going to stick with simple terms and then I'll complicate it later. And if that's the case, then the amount of energy applied to C would be the same energy applied to A plus B, but the result would be as if it was A plus B, and that would be the predictor. Like if you hit an electron with a certain amount of energy, and let's say you hit a proton with the same amount of energy, the proportional velocity, momentum, and energy that the proton receives does not necessarily mean it's going to go half the speed of the electron. There's a whole lot of other things that come into play with particles.